Swayam Prabha. Digital India. Educated India.
Last time we started the study of zero-sum games, and these were games involving two players with finitely many strategies for each player, and we said that they can be represented in this sort of form. Now, a zero-sum game had the property that the payoffs of the players sum to 0. So, as a result, you could represent the game using only one set of payoffs, and that was represented in a matrix form. So, a zero-sum game was represented using a matrix A, where the rows of the matrix were the strategies of player 1, and the columns of the matrix were the strategies of player 2. And player 1 seek to find the least value in the matrix. He wanted the least value, so he was the minimizing player. And player 2 was the maximizing player. And what did we introduced something called as a security strategy for the players. So, the security strategy is the strategy for the row player. Strategy for the row player was a row I star, such that if you take the maximum damage that he could get under I when he plays I star, this was better than what he could get from any other row. Okay. So, I star was a row that satisfied this. Similarly, for the column player, we had a security strategy J star, which was defined with the property that the minimum, again the maximum damage that he could get, which is the minimum over I of ij star, this was greater than equal to the minimum over I of aij for all j. And the significance that I said of security strategies was that the security strategies basically bounded the payoff that a player, bounded the loss that a player could incur. In other words, that if the row player played I star, then the worst case payoff that he could get was this number here, and this was called, if you recall, this was called the security level. The worst case payoff that he could get was this security level. And the reason for that was because if the worst case payoff that he would get would be if the column player played the j that maximized aij star, but if the column player played any other j, okay, then the row player would always be better off, because this was the maximum, and he was looking for, the row player is looking for the least possible value in the matrix. Any other strategy j that the column player played was always beneficial for the row player. So, in particular, so the security strategies satisfy this particular property, that if you look at the max over j of ai star j, this is always greater than equal to ai star j for all j, right. So, what is this here? This term is what the row player's objective, and the column player plays j. So, when the column player plays any j, what the row player can get is only better than the left hand side here, which is his security level. So, the security strategy basically guarantees him a certain level of his objective, that he can always get a number lower than this particular number. So, that is why we denoted this by a notation called V upper bar. V upper bar of A was the min over I max over j of aij. And similarly, there was an analogous one for the column player also. That was the for the column player, we had that the min over I j star, this was always less than equal. This was always less than equal to ai j star for all I, which means if the row player played any strategy, he was the column player was guaranteed to get a payoff greater than equal to this, the left hand side security level payoff. So in other words, if the row player and column player play I star and j star, then they are guaranteed to receive a payoff better than that defined through these security levels. Okay. So that was what we discussed last time, and then we discussed something about saddle points, which I will come to in a moment. But what I want to do now for a little while is to also give you another interpretation of the significance of security strategies and security levels. Okay. So presently we have been assuming that the players are playing simultaneously. So there is no communication between the players, and there is the other player is not aware of what his opponent has played. Okay. But now suppose there is a definite order of play. Okay. Suppose there is a definite order of play. Suppose player 1 plays first, and then player 2 observes his action, observes player 1's action, and then responds to that. Okay. So player 1 chooses a row, player 2 gets to see what that row is, and then decide what column he should be playing. If there is such a definite order of play, then what should the players play? Okay, why is that? Why would the first one play? Why would the row player play his security strategy? Right. So notice this. See, basically now suppose the row player plays, suppose P1 plays first. And he picks, say, a row I. Now this row I is played by player 1. Player 2 can now observe that row I has been played. So what are the choices for player 2? He has to pick a column. Alright. But his payoff is now very well defined, because he knows that it's going to be one of Aij, where I has already been declared to him. Right. So I is known, so he has to look over the columns and says, okay, which is the column that gives me the best payoff. Right. So that column player player 2 will respond with j such that, so the j that maximizes, basically with j that maximizes aij, with I known, remember, with I known. Okay. So player 2 will now pick the j that maximizes aij with I known. Alright. So in other words, player 2 is going to just maximize aij. Now this is what happens when player 1 plays a row I. But player 1 knows that this is what is going to happen, because player 2 is going to be maximizing aij. So he can now choose his row I, so that in anticipation of what is going to happen, right, in anticipation of how player 2 is going to respond. So if he plays row, then what row should he be playing in that case? He should be playing the row I, which minimizes this particular term, which minimizes this term. Right. So he should choose the row I star such that it minimizes the max over j of aij. So in other words, another interpretation for the security strategy is that it is the strategy that the player would have played if he was playing first. Okay, if the row player was playing first, he would have played I star. If the column player was playing first, he would have played his corresponding security strategy J star. Okay. Now, yeah. No. So, player 1 is going to play first. Okay. So, he declares his I. Player 2 responds to that with a J. Right. Now, knowing that this is going to be the response, he can choose the I. So, he minimizes the prospective response that will come up after he chooses the I. Okay. Now, if this was in fact the game, right, if this was in fact the game that player 1 was supposed to play first, follow, and then player 2 was going to has to follow, then this is in fact the solution. There is not much else left to do as far as solving the game is concerned. So, in fact, the security strategy is the strategy to play if there was a definite order of play. Okay, the solution of the game would be that the player playing first plays his security strategy and the other player just responds to that. Yes. No. Yeah, player even if whatever player 2 already knows that player 1 is rational. Okay, so that okay, even if you assume that it makes no difference, because eventually player 2 has this is what is called a fait accompli. Basically, his options are locked once player 1 has already declared his strategy. Player 2 has to basically pick the column that that gives him the best payoff in that row. That's it. Right. Yeah. Okay. So the security strategy therefore can be interpreted as the right solution for a game where the play was sequential. Okay. We will talk more about sequential play much later in the game, but as right now we are this is just more as an artifact for interpreting security strategies. That security strategy is the right strategy you would have played if the game was sequential. Okay. And if there was a predefined definite order of play. What this also means is that it is a strategy in which if the player played in a why am I saying that this is in fact the right solution for this this problem? Because you can think of it this way, that if player 1 plays I star, okay, then he is guaranteed that he will not come back with any regret. He plays I star, he is player 2 will then respond with a column that maximizes this box term here. Player 2 will respond with a column that maximizes this this term with I equal to I star, and therefore then in given that is how player 2 was going to respond, it makes sense that player 1 just picks the I star that minimizes this. If he had picked any other I, not I star, then he would have could have in hindsight regretted that I could have actually, knowing that this is what player 2 was going to respond with, I could have played differently, right. So in other words, this is the right solution concept, because there is exposed after the game, after play has played out, there is nothing for the player nothing for the player to say that he could have done better, right. Now, if there is no definite order of play, right, this situation changes. So let's do an example. Okay. So let us say, for example, consider this. So this is player 2, this is player 1. Matrix is 4, 0, minus 1, 0, minus 1, 3, 1, 2, 1. Okay. Can you find the upper and lower security levels? What is V upper bar? And what are the security strategies for the two players? What is V upper bar here? So how do you find V upper bar? You have to look for the maximum over the column in every row and look for the row that gives you the least value of this maximum. Okay. So let's just do that. Look at the maximum over the columns in this row. What is that? That's here. That in this case it's 4. So I'll just write it here. So what I'm writing here is the max over this over the columns in each row. Okay, max over columns. So this is 4. What about the second row? What is the maximum over the columns? It's 3. What about the third row? The max over the columns is 2. Okay, and now you look for the minimum of these green numbers. So this is going to be equal to 2. Okay. What is V under bar? V under bar, what I need to do is take the minimum over the rows in each column. Okay, so in this column, now what is the minimum over the rows here? First column 0, second column -1, third column -1, and then look at the maximum out of these, okay, which then gives me 0. And what are the security strategies? It's easy to see actually what the security strategies are. What is the security strategy for the row player? What's the strategy that gives him this security level? Third row, row 3. And what about for the column player? Column 1. Right? Suppose now there is no definite order of play, and the players play actually these two strategies, I star and J star. Okay. Now, what would happen if let's take it from the player 1's point of view. What happens if player 1 chooses I star? That means row 3. What does the column player play? Column player would play column 2, right? But if column player was playing column 2, what would the row player have played? Row 2, right? Not row 3, right? So likewise, let's think about it from the column player's point of view. Column player the security strategy is suggesting him to play J star equal to 1, which is column 1. Okay, if he plays column 1, player 1 would respond with row 2, which is 0. He would get 0, right? With row 2. But if player 1 was indeed playing row 2, what would the column player respond with? Column player would respond with column 3, right? So another way to think about it is, suppose the row player plays row I star, thinking that the column player is going to do the worst. Column player plays rows J star, thinking that the row player is going to do the worst possible damage, right? But the worst possible damage to I star is not J star, right? So what's the worst possible damage to I star? It is column 2, right? If player 1 had chosen, if these two players had chosen I star and J star and played this way, each has a reason to regret. That they would each think that, if I knew that this guy was going to play J star, I would have played differently. So if column 1, if player 1 would have, if the column player had played J star, player 2 would not have played I star, right? Player 2 would have played row 2. Player 1 would have played row 2, not row 3, right? Likewise, if player 1 is playing row I star, which is row 3, column player would not have played, could not have played column 1, he would have played column 2, right? So in other words, if you think of this as an I star J star comprising of security strategies, just a pair of security strategies as a solution, it is not satisfactory, simply because there is a reason to regret after the game, right? Which means that there is somewhere you feel that the reasoning process that the players have put in has not given you a satisfactory conclusion. There is something for each player to get that they each think they could have done better, given the circumstances. So which means that there is Now, the reason this has happened in this particular example is because your V upper bar is not equal to V lower bar. Now, that brings me to the other theorem that we proved last time. What did we conclude last time? We concluded that if V upper bar is equal to V lower bar, okay, then there exists a saddle point. What is a saddle point? A saddle point is so what is a saddle point? A saddle point is a pair of strategies I star j star such that A I j star. So A I star, if you look at it from the point of view of player I, so from the point of view of the row player, the row player is better off playing I star in response to j star, okay, and the column player is better off playing j star in response to I star. Right. So, if V upper bar is equal to V lower bar, then there exists a saddle point. In that, once there exists a saddle point, the kind of regret that we just saw above doesn't exist. Right. Now, moreover, so but there is a slight catch here, which so this is for all I and for all j. So there is a slight catch. I said I star j star is a saddle point, but what is the guarantee that this saddle point is in fact the same as the same I star j star for that we wrote above for security strategies, right? Because I was talking of regret from in terms of security strategies, but you can, but actually but what's very nice is actually that the saddle point in fact comprises of security strategies. So, and in fact the converse is, so this is what we showed, and actually if you see the proof that we discussed last time, you will see that the converse is also true. That means if there is a saddle point, then V upper bar and V lower bar become equal. So, here the way I have written it is that if V upper bar is equal to V lower bar, then there exists a saddle point, and the saddle point comprises of security strategies, and the opposite result is that if there exists a saddle point, then V upper bar is equal to V lower bar, and that is actually equal to A I star j star. If there exists a saddle point I star j star, then these are equal. Okay, any questions about this? Yeah. Yes. So, a saddle point is actually the same as the Nash equilibrium when applied to zero sum games. You can see, in fact, you can see it from this inequality here. Each player, the way you can think of it as a Nash equilibrium, as you can say that assuming the other player plays his start strategy, each player would want to play his own starts, would not want to deviate from his start strategy, right? So, so I'll write this here. So saddle point is a Nash equilibrium is basically equivalent to Nash equilibrium for zero sum games. Now, here's something to just take note here. See, if the way the saddle point is defined is that it requires you to define that pair. Okay, and in fact, this definition of saddle point is exactly what you encounter when you do calculus, multivariable calculus, optimization, saddle points, and so on. Okay, so the saddle point requires you to define the pair I star j star. Security strategies did not require you to concern yourself with what the other player is going to play. Security strategy was just defined as in this way, the mean over the I star that minimizes the max over j aij, and the j star that maximizes the min over I of aij. So I don't really need to know what the other component of the component is. If I want to find the security strategy, all I have to do is this. I don't need the j star to find the I star, and likewise I don't need the I star to find the j star. Whereas in a saddle point always is defined with I star j star as a pair together. The pair is called a saddle point if this inequality, they together need to satisfy these two inequalities, right. So a saddle point in some sense is a more demanding concept, but a security strategy is something that each player can compute on its own. Doesn't need the, I don't need to even take the view of an observer. It's just each player has to just compute a security strategy by its own calculation. Okay, so that is one thing. So the security now the security strategies can be computed by players independently. A saddle point is something that is a joint definition. Okay, but when V upper bar is equal to V lower bar, the two coincide. Okay, a saddle point comprises of security strategies and vice versa. This is what happens when V upper bar is equal to V lower bar, which means if the game satisfies V upper bar equals V lower bar, then in that case players can basically reason about the game sort of in some sense independently. Each player basically just thinks of the worst that could happen and plays, and that turns out to be zero regret or satisfactory at the end of it all. Okay, unlike in the reason I brought this up is because the comparison with the Nash equilibrium game. The Nash equilibrium, remember, is something that is defined as a profile. It's a profile of strategies for the player such that no player has an incentive to deviate. So for that, the entire profile has to be defined together. You cannot define each player's action independently. If you go back and think about the deer rabbit game, for example, I can't think of only one player's strategy as deer and another player's strategy as rabbit and think of those two as separate, because then that will not, I cannot deer is a Nash equilibrium there, rabbit is a Nash equilibrium, but deer rabbit and rabbit deer are not. Okay, so this is again a peculiar structure of the zero-sum game. The zero-sum game has all these nice properties that, it's essentially because players are this kind of, are into mortal combat here. That's the reason why this is happening, because they are basically just out to kill each other. Any gain to one is lost to the other. Okay, so that is why there is this particular, all this structure prevails. Here is another corollary of all this. Now, since a saddle point must always comprise of security strategies, whenever V upper bar is equal to V lower bar, saddle point must comprise of security strategies. But as I said, security strategies can be computed by each player separately, which means these two quantities, V upper bar and V lower bar, can be computed by the players separately. In other words, they are properties of the matrix itself, right? They are not properties of the specific saddle point necessarily, because the saddle point is just a pair that satisfies this, whereas these two quantities, whenever a saddle point exists, its value actually ends up being equal to the V upper bar and V lower bar, and these two are actually functions of the matrix, which means, what does this mean? Which means all saddle points must have the same value, because they end up being equal to V upper bar and V lower bar, right? Yeah. So corollary here is all saddle points have the same value. Now this is in itself significant, because what it is saying is that even if there are multiple saddle points to the game, it doesn't matter which one you pick, the value that each player gets is the same, regardless of what that saddle point is. Okay. Again, contrast with the deer rabbit game. Deer gave you a different payoff, rabbit gave you a different payoff. There are two different Nash equilibria which gave two different payoffs to both players, right. On the other hand, in a zero sum game, once there is a saddle point, there is one saddle point regardless of what the structure of the matrix is. Once there is a saddle point, it has to be that all saddle points will give you the same value, provided there exists a saddle point. Okay. So, this again simplifies for us, as observers of the game. This tells us, this is very useful because it tells us that there is, I may not be able to predict the saddle point, but I can certainly predict what the value each player is going to get. Yeah, I can say something very definite about what value each player is going to get. Okay, all right. So that's that. So all saddle points have the same value. Here is another corollary of what I just wrote on the previous page. Now, suppose there are two saddle points. Let's say I1 J1 is a saddle point and I2 J2 is another saddle point. So, if J1 and I2 J2 are saddle points. So, these are saddle points. Now, therefore, what does this mean? Every saddle point must comprise of security strategies, which means I1 is a security strategy for player 1, I2 is also a security strategy for player 1, J1 is a security strategy for player 2 and J2 is also a security strategy for player 2. But then what did we also say? That if there is a saddle point, then every pair of security strategies is also a saddle point, which means I1 J2 is also a saddle point and I2 J1 is also a saddle point. So that is, so if there, so actually, yeah, you'll have to go back to the previous, the proof that we showed at the end of the last class. Essentially, if V1 equals V2, there is a saddle point and saddle point comprises of security strategy. So conversely, if a saddle point exists, okay, then V1 equals V2, and then once V1 equals V2, the saddle point becomes is comprised of security strategies. So and you put together any pair of security strategies, they have to be a saddle point, because security strategies give you V1, V upper bar and not V1, V2, what am I saying? V upper bar and V lower bar, right? Okay. So if I1 J1 and I2 J2 are saddle points, then so are I2 J1 and I1 J2. Okay. What this means is, this is what is called the interchangeability. Changeability of saddle points. What this again means is, see again, remember in the deer rabbit game, deer was a Nash equilibrium, rabbit was a Nash equilibrium, but deer rabbit is not, right? But in a zero sum game, you see what has happened. You can take one player's strategy from a saddle point, combine it with the other player's strategy from another saddle point, and put those together. That still remains a saddle point. Okay, this kind of mix and match that you can do here with player strategies is essentially because the way a saddle point is arrived at is by both players kind of independently reasoning. You don't have to define the pair together if the saddle point exists, because it comes out from security strategy. Yes. Yeah, I think that generically it should be possible. I don't know if I have a numerical example. Yeah, but you see, I mean, so simple. Okay, I can give a pathological example. I can just repeat the last row. So I can just create one more row, copy paste this last row here. It would be either row 3 or row 4. Yeah, values would be same. I mean, but here, this is a bad example because there is no saddle point here to begin with. Okay, here we didn't have V upper bar and V lower, but nonetheless, I mean, just imagine a game where you had a saddle point and you just duplicated the row that had the saddle point, right? You will get, or the column that had the saddle point, you will get this particular property. So, mathematically, I mean, that is of course a very kind of contrived example, but mathematically there could very well be multiple rows that give you the same worst case payoff, or likewise multiple columns that give the same worst case payoff. So, if there is this, because of this interchangeability property, essentially how to play, in a zero sum game has a very simple answer. Just if V upper bar is equal to V lower, what you need to do is just play your security strategy, and that's it. That is the it doesn't matter whether which security strategy other guy is going to play. You would get the same payoff regardless. Okay. So this is basically the let's say where this is essentially what you can say is how you would reason if V upper bar is equal to V lower bar for a zero sum game.